Okay, this is our MMPS task 2, and the question is, can someone throw a ball over a house, run through the house, and catch the ball on the other side? So before we even begin this problem, there are a list of things we need to consider, and these are the different factors that can affect the model that we create. In order for us to develop a basic model, we need to make assumptions about how the model will work, and the list of the assumptions can be seen on the PowerPoint. As well as this, we also need to let the height of the house be a value and the length of the house be a value. From research and our common sense, we decided the height of the house to be 10 metres and the length of the house to be 20 metres. We also decided that the distance the cricketer stands from the house to be 10 metres. As you can see, these are the images that we used, the 3 images that we used to base our basic model on. Image 1 shows a simple diagram that the cricketer must get from 1 to 2 before the ball gets from 1 to 2. Image 2 shows the projectile motion graph. We decided to split up how the ball will travel into the x and y axis, and on y would be u sine theta and on x would be u cos theta. And image 3 shows a more detailed image of the model.
These are the SUVAT equations that you learn at A level, and these are the ones we use to develop our model, particularly the 4th equation.
So in order for us to start our basic model, we found 3 basic inequalities that must be met. Using the projectile motion formula, as well as the SUVAT equations, we can compile 2 formulas for x and y, which also can be shown. Then we can substitute t into the equation y, and we get y equals x tan theta minus gx squared all over 2u squared cos squared theta. Because the vertical displacement of the ball at this point is 0, we decided to make y equals 0 and rearrange the equation to get what is shown on the board. Rearranging this using the standard trigonometric identities, we found an equation in terms of x, which can also be seen on the slideshow. So in order to get values from this model, we must make assumptions and decide on certain values, as these equations have too many unknowns to calculate otherwise. Following research and using common sense, we chose values of the height and the x values, and the initial velocity and the speed of the cricketer, which can be shown here. Then, using our projectile motion formula horizontally, we found that for the cricketer to be faster than the ball, he would need to satisfy the following inequality. Using the 3 inequalities that we started off with to make sure the ball passes the house and substituting in our chosen x, h and u values, we found a range of theta values for each inequality and chose values that satisfied all 3 of the inequalities. From these graphs, we found out a range of theta values, and this range is where it's positive in the y-axis. We substituted this range into our y and x equations so that we could find out whether or not the cricketer would make the run in time and whether or not the model will work. For our minimum value of theta of 0.82, we get a time and an x3 value that both hold, but unfortunately the inequality p does not hold, which means the cricketer fails to make it. Similarly, for our maximum value of theta of 1.04, this is the same, as t and x3 both hold, but the inequality does not. So what would happen if the cricketer could bowl at world record speed? Well, the world record speed is 40 metres per second. As you can see, we've used the same concept as before with the 3 graphs, and these graphs show our possible theta values where the ball will make it. Again, using the same concept as before, we found a range of theta values, and for our minimum theta value of 0.71, the time and the x3 value both held, but the inequality p did not. Our maximum value of 1.47 does not make it either, but not for the same reasons. This time, our inequality p does hold, but it's the x3 value that's the problem, as the x3 value becomes negative, suggesting that the ball will not surpass the house. Fortunately, however, we did find a range of values within our original range that will satisfy the inequality and also x3 and our t value. We found this range within the range to be between 1.37 radians and 1.44 radians. Thus, if the cricketer threw at 40 metres per second and ran at a constant speed of 8 metres per second, within these angles, he would make it. But whilst this is the world record speed, it is unlikely that he's able to throw at this speed. So we decided to take an average between 20 and 40 and made u equals 30. At this u value of 30, we found a range of angles between 1.31 radians and 1.39 radians that will work. So ultimately then, our conclusion is that the task can be achieved by the cricketer, but it's very unlikely it's going to be able to do so. As for our model, it works realistically, but it's very simplistic. If we wanted to make it more complicated, we would have to include more maths and considerably less assumptions, and this would be way beyond the scope of our knowledge and that of an A-level student. If we did want to take it further, however, then we would have to include assumptions such as air resistance, flight path and the running speed, which would make a more reliable answer.